Good afternoon, everybody. So we get to talk about the entire rest of the universe today. I hope you had a good holiday. I hope you had a good time to rest and catch up with family and friends and catch up with your classes. And you're ready for your final week of classes. So let me tell you just a couple of things. A reminder that this is a normal, regular week of classes. You will have discussion sections. You will have a quiz based on homework number 9 during your discussion. And it's your last one. Remember that you're allowed to miss one without any penalty. So, but if you do take all of your quizzes, then your lowest score will be dropped. So this is your last chance to go. There will be a homework number 10 that I will post on Friday. That one you will not have a quiz for. And the only reason I'm posting it is because the homework is your best study guide for the final exam. So if, so please download it and look at the questions and use it to study for your final, but you will not have a quiz for that. And speaking of the final, well, I'll tell you about the final in a second, but I asked last time for input about whether people wanted an online or in-person review, and a little more, maybe 60% of people wanted an online review. And as it turns out, I can't find a room that is sufficiently large for me to hold an in-person review. So I will keep trying, but for now, I think I've decided that I will do an online review. So it will be on Zoom on this address. I will give an announcement. And I decided Sunday, and I hate to do something on Sunday, but Sunday, December 5th, that's a time when nobody's taking exams. It's a time where everyone should be able to do it. So I'm thinking Sunday evening. Also, by then, hopefully, I will have finished writing the test and I will know what to emphasize. So just keep that in mind that I will be announcing that. About the final is in person. It'll be on Wednesday. So next week, Wednesday at 3 p.m. From 3 to 6, you will have 3 hours to answer your questions. It's about 100 multiple choice questions. Most people will finish in a lot less than 3 hours, probably an hour and a half at the most, but it will give you the 3 hours. The form that you have to use, I have a picture right here, is Scantron form 289 Part L. It's, if possible, please get the one that has this symbol here, Scantron. There are some that they sell online. I saw them on Amazon, and they say compatible with. And in the past, we've had some issues with those forms. Sometimes they get marked wrong by the machines. So if possible, please get the right one, because otherwise what happens is the TAs end up having to transcribe every single one of the answers one by one, and that's a lot of work to give them. So you can find it at the UCR bookstore. You can get it for free at ASUCR. It's on the hub. So this is a map of campus. Here's the hub with all the different food places. And then right next to it is the university bookstore. If you go down the hill down here, that's where the university lecture hall is. And also here on the hub, on the second floor, there's the office for ASUCR. So that's where you can get Blue Books and Scantrons for free. And you should take advantage of that. And will I post a review afterwards? Yeah, I mean, that's one of the advantages of doing the review online, that I will be able to just post it like I do with lectures. The disadvantage is that it's a lot less personal, and I will try to write on, I like to do reviews on the board. I like to draw things and write things. So I'm gonna try to do it on a tablet. But it's not quite the same. So it's not That's the disadvantage, but the advantage again is that I'll be able to post it and you guys will be able to see it. The Scantrons, yes, the Scantrons are free if you go to ASUCR. They cost something at the bookstore. I don't know how much, but probably less than $1 for the Scantron. Yeah, okay. All right, so I'll answer other questions later. Very good. So that's it for the announcements. And let's move on to the very last week of classes. Oh, one more announcement was, yes, if you can fill out an evaluation for this class, it is much appreciated. And I take your feedback very seriously. So, okay. All right, so we've gone on a tour of the universe, and mostly in this class, I have I've actually emphasized or spent most of the time in this class talking about things that are relatively close. And I know that sounds crazy when the types of distances that we talk about, the distance from Earth to the sun and to the nearest star and how large our galaxy is. But for astronomers, all of that actually sounds very close to us. And there are other classes like Physics 20, Physics 5 in particular, that deal with things that are much, much further away, such as clusters of galaxies and galaxies that are billions of light years away. If you guys are interested in those type of topics, the topics that we're going to cover this 1 week, I recommend that you take another class, like I said, Physics 20, Physics, especially Physics 5, and also Physics 39, I think it is. It's called Origins. Those all deal with the stuff that we're only going to cover just a tiny bit. So we're going to be talking about the universe as a whole, about what we know about the entire cosmos, and a little bit about the ideas of how the universe formed, how it started, and then how it's going to end. So for today, we're just going to talk about astronomical observations, things that led to the discovery that, one, the universe is expanding, that the universe had a beginning, right? It wasn't always there. There was a time when there was no universe. And in fact, there was a time when there was no time. And then I think on Wednesday, we will cover how there is a limit to how far we can see. And it's not just given by what kind of telescopes we have. It has to do with the fact that the universe is expanding. So let me get right into it. Let me just, we're going to be talking a lot about redshift today. And let me just remind you that redshift referred to the Doppler shift of light to longer wavelengths, right? When light that was originally blue becomes redder, or blue becomes green, or green becomes red, or light that was red becomes infrared. This is when the waves are stretched. They become longer, and so we see it as being shifted toward the red or shifted toward longer wavelengths. We talked about 2 cases of this already. So we talked about a case where this happens because a source, the source of light, is moving away from us or receding. We also talked about it when light experience a lot of gravity. So in a very strong gravitational fields such as the one near a black hole, light gets also stretched. Today, we're going to talk about a third aspect of redshift, right? And this is when light becomes stretched, the wavelengths become stretched also because the universe is expanding. But for now, let's just think about redshift the way that we learned it at the beginning, with exoplanets. When we were talking about how when the star is going toward us, light gets shifted to the blue, and when the star is going away from us, then it gets shifted toward the red. And you can see the example here, how I told you that the light, when you spread it in a spectrum, it looks like a rainbow. And then there are certain features that we can see how they move back and forth depending on whether the star was moving toward us or away from us. And by measuring this shift, we could figure out the velocity. Same thing with measuring the mass of black holes, for example. So we could measure, thanks to that redshift or blue shift, we could measure the velocity and then other things. So in the same way, let me move back to a little less than 100 years ago. So in the 1920s, I already told you the 1920s was a very exciting decade for astronomy, because that's when they discovered that the Milky Way was not the only galaxy. There were many other galaxies in the universe. Well, the other thing that they discovered was that not only were there a lot of galaxies outside of the Milky Way, they also seemed to be all experiencing this redshift. So let me just give you the example here. So let's say that we take the spectrum, right? We disperse the light into a rainbow, into all the different wavelengths of a single star that is near us and that is not moving away from us. Like I said, it has, all the colors, but it also has certain features, and these are units of nanometers. You don't need to know that, but at certain wavelengths, you see certain dark features. They're called absorption lines. What they discovered was that when you look at a galaxy, which is made of many stars, you see a very similar spectrum. You see this very similar, rainbow with the dark features, but they seem to be a little bit displaced toward the red, right? So shifted toward longer wavelengths. And then if you were to observe other galaxies that were further and further, right? So same like another galaxy also made of stars, and you see it, here it looks smaller because it's farther away. Then the lines were even more shifted. And then as you go to further and further until the galaxy is just a tiny little smudge, then those lines, the same lines, right? I mean, this line here shifts over here, shifts over here, and over here, you can't even see it anymore. You can see how all the features keep getting shifted and shifted toward the red. What Edwin Hubble discovered was that there was a correlation. The further the galaxy was, the more shifted toward the red all these features appear. And so it seemed as if the spectral features of all galaxies in the universe, all the ones that he was observing, were shifted toward the red or red shifted. And so the conclusion was, well, galaxies must be moving away from us. So here's Edwin Hubble at the telescope. And here's an example. He was looking at various different galaxies, right? And so this is just simulating, how, like, let's say these two features, how they move to different parts. They move toward the red. And so what Edwin Hubble did is he plotted them. This is something we always do in astronomy. We love measuring things and then just plotting them and see if we find any correlations. And so the way that it works is we measure through some independent method, which you can learn about in Physics 20, for example, but we measure the distance from us to the galaxy, and we plot it on the x-axis, distance to the galaxy. And then we take a spectrum and we measure the redshift, meaning how far to the red are these lines shifted. We can get a velocity from that. So for those of you who like math, it's a very simple mathematical arithmetic, basically. So you take the wavelength that you measure, you subtract the wavelength of the feature that you would measure in the lab, you divide it by the wavelength you would measure in the lab, and then you multiply it times the speed of light. Okay, people who don't care about this, it's okay. The point is you can get a velocity or a speed very easily. And so if you plot it, if you plot the distance to the galaxy and the speed that you measure from the redshift, what you end up finding is that there is a correlation. There is some scatter, right? It's not a perfect line, but it's very, very obvious that galaxies that are farther away, right, larger distance, also have a larger velocity. So this is what came to be known as the Hubble law or Hubble's law. And what it says is that on average, right, give or take, there's some scatter, but on average, the recession velocity, the velocity at which the galaxy is going away from us, is directly proportional to the distance to that galaxy, right, from us to the galaxy. So that is what is called Hubble law. And again, this is something that happened in 1929, and it kind of revolutionized our view of the universe, because the conclusion was that all galaxies were moving away from us. We will see later in the class that they're not actually moving away from us, but they seem to be moving away from us, and not with random velocities. The farther they are from us, the faster that they appear to be moving away from us. And if they're closer, then they appear to be moving at a slower velocity. So whenever you find a correlation like this in science, you always ask why, right? There has to be some model that you can construct that would result into these observations, right? Like what's happening to the universe that makes it seem such that you look at galaxies and they're all moving away from you, and the further they are from you, the faster they're going. There has to be some explanation, and that's what we're going to talk about next. So let me just tell you in terms of, in mathematical terms, the Hubble law or Hubble's law is just the velocity is equal to a constant times the distance, right? So this is just the equation of a line. So if you guys remember from those of you who learned about this in high school, y equals mx, so y-axis, the value in y is equal to the value in x times the slope of the line, right? So that's, what's the y-axis is velocity, what's the x-axis is distance, and then there is a constant, which is the slope. And for this particular line, the h0 or h0 is called the Hubble constant. And it is a very important constant in astronomy, and I will get back to why. But this is just the way that it was done by Hubble, and astronomers have kept trying to refine the observations of this particular line, of this particular relation, for the next 90 years, right? I mean, until today, we're still trying to get measurements of galaxies that are further and further, because as we will see on our next class, what happens to the universe at the end actually depends on the slope of this line. And how old the universe is depends also on the slope of this line. So it's a very important line, right? It seems like a simple thing, but it is very important. All right, so let me ask you this. So it seems like every galaxy is moving away from us. So does that mean that we are at the center of the universe, right? So no, not this one. Okay, so if every galaxy is moving away from us, does that mean that we are at the center of the universe? Would you conclude, if you saw that every galaxy is going away from you, would you conclude, or, well, not would you conclude, because some people would, are we at the center of the universe? All right. So the majority of you decided that no, we are not at the center of the universe. All right, that's correct. We are not at the center of the universe. But it's not obvious, right? It's not obvious why. And I'm gonna try to guide you through why that is not the case. So first answer that I will give you, why are we, if we are at the center of the universe, why does it seem like everything is going away from us? Well, first of all, we cannot be at the center of the universe because there is no center of the universe. Why? Okay, so let me introduce to you the cosmological principle. Cosmological principle says that the universe looks about the same no matter where you are within it. So what does that mean? It means that matter and light and everything that is in the universe, you know, dark matter, regular matter, energy, is evenly distributed in the universe on very large scales. I mean, obviously, if you look at small scales, well, there's a place where there is a galaxy and then there's no galaxy. So obviously, it's not evenly distributed in a small scale. But if you go to very large scales, where you zoom out, and in this plot that comes from a YouTube video, in this plot, like all of these that look like bubbles, those are, they're called filaments. And those are regions where you get a lot of galaxies that are lined up. And if you zoom out to very large distances, you see that this looks pretty uniform, right? Meaning there are no more galaxies on the right side than on the left, for example. It's even. So this is a the cosmological principle here has not been proved. This is a principle. This is something, sometimes in order to study something, you have to make some assumptions. And then you go with that assumption until proved wrong. In the meantime, you just assume that it is correct. And that's what we do with the cosmological principle. We assume that the universe is uniform, that it is about the same, regardless of where you are. Now, that means that if you're sitting where my cursor is, right in the middle, you would see this, on average, the same number of galaxies on top, on one side, on the other, and on the other side. Well, this implies that there cannot be edges to the universe, because if you sit here, right, I'm on the right lower corner, you should also see the same number of galaxies on this side than you see on the right, and you see on the bottom. If there was an edge, then you wouldn't see any more galaxies on that side. So it needs to be of infinite extent, right? Or maybe not infinite, but at least folded in such a way that you would see the same amount of galaxies regardless of which way you looked at. So the cosmological principle implies that there are no edges. And you can't have a center if you do not have edges, right? So if I have a notebook and I'm trying to figure out where is the center of my notebook, right? Well, what I do is I measure from one edge to the other and I go halfway, and then from one edge to the other and I go halfway, and that's how I find the center. But if there's no edges, then there cannot be a center. There's no center. So if the universe does not, can I repeat why there are no edges? I think we have a little bit of a delay. So there are no edges. Maybe you just want me to clarify. All right. Imagine that the universe has edges. It doesn't, but imagine that it does, right? So like here, let's say this is the edge of the universe. According to the cosmological principle, if you were to sit in a galaxy right here where my cursor is, I should be able to see the same number of galaxies in this direction, you know, above, than below. But if it's an edge, that is not true, right? Like if you're in a crowd of people, if you're at the edge of the crowd, you look one way, there's a lot of people. You look the other way, there's nobody. And that would violate the cosmological principle. The cosmological principle says that the universe looks the same no matter where you are within it. That means you cannot have an edge, because an edge would imply that this is not true, that the universe doesn't look the same wherever you are, because you look one way and it looks like there's no galaxies. You look the other way and it looks like there are a lot of galaxies. So that's why the cosmological principle implies that there are no edges. And if you don't have edges, then therefore you can't have a center. And again, this has not been proved. It is just consistent with all the observations that we have to date. And we keep testing, right? So we make models and we make numerical simulations, and then we try to reproduce what we see in the universe. And we take this cosmological principle and we apply it to those models. If it ever fails, then we will come back and we will revise this. We will be like, oh, oops, I guess the cosmological principle is not true, or it doesn't work. So, and with everything, I mean, everything that I've taught in this class up until now, that is always true. We have a hypothesis, we have a working theory, a working model, and it works, and we keep testing it. And then if it ever fails, then we need to revise it. And that's how science is done. All right, so the universe has no edge and it has no center, as far as we can tell, as far as we know. So if there is no center, then why does it look like all galaxies are going away from us? All right, so let me play this video.
Einstein's equations of general relativity describe space and time as a kind of interconnected fabric for the universe. This means that what we know of as space and time exist only as part of the universe and not beyond it. Now, when everyday objects expand, they move out into more space. But if there is no such thing as space to expand into, what does expanding even mean? In 1929, Edwin Hubble's astronomy observations gave us a definitive answer. His survey of the night sky found all faraway galaxies recede or move away from the Earth. Moreover, the further the galaxy, the faster it recedes. How can we interpret this? Consider a loaf of raisin bread rising in the oven. The batter rises by the same amount between each and every raisin. If we think of raisins as a stand-in for galaxies and batter as the space between them, we can imagine that the stretching or expansion of intergalactic space will make the galaxies recede from each other. And for any galaxy, its faraway neighbours will recede a larger distance than the nearby ones in the same amount of time. Sure enough, the equations of general relativity predict a cosmic tug-of-war between gravity and expansion. It's only in the dark void between galaxies where expansion wins out and space stretches. So there's our answer. The universe is expanding unto itself. That said, cosmologists are pushing the limit of mathematical models to speculate on what, if anything, exists beyond our space-time. These aren't wild guesses, but hypotheses that tackle kinks in the scientific theory of the Big Bang. The Big Bang.
All right, so I like that analogy that the universe is represented by a cake, right? Like by the dough. And then there's chocolate chips or raisins or whatever, and they are and they represent galaxies. So if you have this cookie, or no, this cake, and you have chocolate chips that are evenly spaced, as the cake rises, as the dough expands, each one of the chocolate chips in this case is going to move away from each other. And if you saw this from the perspective of the, chocolate chip number 3, you would see that 2 and 4 and 1 and 5, they're all going away from you. But the same is true if you go to number 5. Number 5 also sees everyone as going far away from each other. This is an imperfect analogy, like many of the analogies that I give you in this class, because of course, this cake has edges and it has a center. So it doesn't work. With the universe, you wouldn't have any edges, you wouldn't have any center. But the idea is, if space is the thing that is expanding and the raisins are just traveling along with the expansion, they're not really moving, right? They're just sitting there. It's just that the cake is expanding. And so that carries them away from each other. So now putting it in terms of galaxies, you think about the expansion as seen from the perspective of this galaxy. You see as the space expands evenly, all of the galaxies are going to appear to be moving away from each other. And of course, the one that is already farther away, since it's, let's say the space doubles. So it started by being 2 million light years, and in a given amount of time, if it doubles, it'll be 4 million light years away from it. So it looks like it's going faster because in a given amount of time, it traveled, quote unquote, 2 million light years, right? Whereas this one that is closer, it started at 1 million, the space doubles. Well, it ends at 2 million, right? One that was 10 million light years away, if the space doubles in a given amount of time, it'll end up being, I said 10, it'll be 20 million light years. So it seems like it traveled a lot more. But all that is happening is just that this space is expanding, and it's expanding uniformly everywhere. And so the galaxies that are held together by gravity, right? Gravity is keeping them from also expanding. They're just carried with this expanding space. And so they seem like they're moving away from each other. So here it is, sort of the same example written in words. All right, so that concludes that galaxies are not really moving away from each other. It is space in between them that is expanding. Now, Hubble law, all that it does is it is describing how there is this continuous expansion of the universe, or continuing. And so the redshift that we measure, right, that Doppler shift toward the red, is not that the galaxies are moving away from, I mean, they are sort of moving away, but that's just because the universe is expanding. But what it is as light travels, the wavelength of light gets expanded also with the expansion of the universe. And that's why light gets redshifted. I have a question about whether Andromeda, like how come? Isn't Andromeda coming toward the Milky Way? We talked about that in our last class. That is correct. So Andromeda is actually moving toward us, not away from us. Why? Because the gravity of our Milky Way and Andromeda is stronger, or it's like holding them together against the current, right? Against the current of the universe expanding. The video that I just showed mentioned very briefly that it is a tug of war where you have gravity competing with expansion. And in short scales, right, where gravity is stronger, gravity will win, right? Gravity is keeping clusters of galaxies together. So a cluster of the galaxies are not moving away from each other. They're sort of staying together. The picture that is coming to my mind as I'm talking about this is like sea otters. I don't know if you guys have seen them when they sleep. Sea otters, they sleep on the surface of water and there's current. and they actually hold hands, which is like adorable. So sea otters hold each other's hands so that when the current comes, they are not split apart. They stay together. So think about galaxies, and you should Google sea otters holding hands because they're really cute. So, and don't do it right now, wait until the end of the class. So you have two sea otters, or two galaxies. Their holding hands is the gravity. So even though there's the current, which would be the expansion of the universe, the two galaxies will actually stay together because of gravity. And also the stars within a galaxy, they'll stay together because of gravity. But when you go to longer distances where gravity drops, right? Because gravity drops with distance. So when the force of gravity is not as strong, then the expansion of the universe kind of wins and causes them to, causes the distance to become greater between galaxies. So thank you for the question. It's very good. So going back to redshift, the redshifts that we see from distant galaxies are caused by the expansion of the universe, the expansion of space, and not by actual motions of galaxies going through space. But it looks the same, right? So that's why it's a little hard to make the distinction. So it is like if the wavelength is traveling in space, and space gets stretched. So the wavelength becomes longer, right? Like shorter, it looks bluer, longer, it looks redder. So as light travels through space, it gets stretched and it gets redshifted. So this is what we call cosmological redshift. So cosmological redshift is just the shifting toward longer wavelengths of light from remote galaxies due to the expansion of the universe. So we talked before about gravitational redshift. And gravitational redshift was when light got shifted toward longer wavelengths because light was experiencing strong gravity. So this is a little bit different, or it's a different way in which redshift is shown, right? I mean, it's a little different. It's cosmological redshift is same thing. Light is, the wavelength of light gets stretched, it becomes longer, but it is because space itself is being expanded, right? It's expanding. All right. All right, so, just what I've been talking about, right? So imagine you have two galaxies and they are emitting light, right? And as they travel, so it starts off, like in this case, it's kind of blue. And as it travels, space is expanding. And by the time it gets to the observers that are at the other galaxy, the wavelength has stretched and it has become longer wavelength. So, right. All right, so in the last 9 minutes, I'm going to try to make a point that the fact that the Hubble, that Hubble law, like the idea that the universe is expanding, implies that the universe actually had a beginning. And I don't really have time to show this, but I can say it in words. If you think about the universe, okay, everything is getting farther away. Every galaxy is getting farther away from each other because of the expansion of the universe. You can sort of rewind, right? And play the movie backwards. And so you can imagine how in the past, things were closer together. And if you go even further back, well, things were much closer together. And you can just extrapolate to the point where everything must have been on top of each other. There must have been a point where the entire universe, the entire infinite universe, would have been in a single point. And so it can't keep going, right? How much smaller can it get? There has to be a limit. And so for that reason, the fact that the universe is expanding now, it implies that it couldn't have been forever ago, right? There had to be a beginning. There had to be a moment when everything started expanding. So let me try to put it a little bit in mathematical terms, like how we figure this out. So if you know how fast something is traveling, and you know how far it has traveled, I'm going to sound like a physics problem here, then you can figure out how long it has been traveling, right? If you know how fast something is going, if you know its speed, and you know how far it has gone, then you can do the math and you can figure out how long it's been traveling. So here's an example. And in fact, let me do it simultaneously here with a problem. So your friend leaves your house. She later calls you, and then she tells you, hey, I've been driving for 60 miles. I mean, I've been driving at a speed of 60 miles an hour. It's great. There's no traffic. And I've been going away from your house in a straight line. I haven't stopped. I am just going constantly, going at 60 miles an hour. And right now, I'm 60 miles away from you. So how long have I been traveling? And it's kind of a silly problem, right? Because usually you know when your friend leaves. But if this were the case, I don't know, you fell asleep and you don't know when she left. And she's been driving at 60 miles per hour, and now she is 60 miles away from you. When did she leave? All right, and people who actually answered say that she left 1 hour ago, which is the correct answer. So your friend left your house traveling at 60 miles an hour. She is now at 60 miles away from you. When did she leave your house? An hour ago is the right answer. How did you guys know that that was the answer? It's sort of simple math, right? Math tells you that velocity is calculated by dividing the distance over time. In this case, you know the velocity is 60 miles an hour. You know the distance, it's 60 miles. So you solve for time, right? So you solve for time. Time is just equal to distance over velocity. So you plug in distance is 60 miles. You plug in velocity is 60 miles away. You plug in velocity, which is 60 miles per hour. So 60 over 60 gives you 1 hour. All right, so that's how you figure this out. Let's say that, so there's your friend who is 60 miles away from you, 60 miles per hour. And then you get another phone call from a friend who actually left on a bike. And your friend tells you, I've been traveling at 20 miles per hour and now I'm 20 miles away. And someone was running at 7 miles an hour and now they're 7 miles away. And then somebody's walking at 3 miles an hour and now they're 3 miles away. So you do the math for all of those and you plug it in and then you solve for time. What you find out is that it looks like there was a party in your house and it ended an hour ago because everyone seems to have left at this at the same time. I think I just ate a mosquito. Excuse me. All right, again, this is a silly exercise because you usually know when people leave your house, but let's just say that you had dementia or, you know, something like you fell asleep and you don't know what happened and you're like, wow, all these people are traveling away from my house. And it seems like if I do the math for all of them, it seems like they were all in my house 1 hour ago. We do the same with galaxies. We observe a galaxy that is moving away from you. Again, it's not really moving away, but due to the expansion of the universe, it looks like it's moving away from you at a certain speed. And that speed let's say it's 0.1 light years per year, and now the galaxy is 1.4 billion light years away from you. How long has it taken to get there, right? So you do the same math, you do 1.4 billion light years divided by 0.1 light years per year, which is the velocity, and you end up with an answer of 14 billion years. So it seems like 14 billion years ago, this galaxy was right here, right on top of us. And what Hubble's law does, if you take also, let me show you the Hubble diagram again. Here, so you get the distance for all the galaxies, and you get their velocities. You can just divide one by the other, and it gives you the time at which the galaxy was right here. And when you do that with all of them, you apply the same calculation to every galaxy in the universe, and you get the same result. And it turns out that for every galaxy, if you apply this math, you figure out that 14 billion years, or to be more precise, it's 13.7, but I'll just ask you to remember 14 billion years. 14 billion years ago, it seems like every galaxy was in the same place at the same time. So this amount of time is called the Hubble time. We call it 14 billion years is a Hubble time. The reason why it is called the Hubble time is because it is calculated from the velocities and the distances from the Hubble law, right? That plot that I just showed you. So we infer that about one Hubble time ago, meaning about 14 billion years ago, all matter was located together in an infinitely dense cosmic singularity. And I know that sounds a lot like a black hole, but it really is actually more like a white hole. Is it a white hole? You can actually Google that, and you'll see they explain to you what's the difference between a white hole and the Big Bang. But there are similarities for sure. But the point is, we infer, right? We don't observe it, but we infer that about 14 billion years ago, everything in the universe, all matter, all energy, all everything was located together in an infinitely dense cosmic singularity. And then at that point, it began to expand. And that expansion began in an event that is called the Big Bang, and that will be the subject of our class on Wednesday. But the thing that I really want to emphasize before you leave is there was a moment when all of this started, right? It wasn't there before. And it wasn't just space that started, it was space and time. Remember, it's sort of like intertwined together. So when people ask, well, what happened before the Big Bang? Well, there was no before, because there was no time. There was a time when there was no time. There was a moment when time began. There was a moment when space began, but nothing before. I personally find this incredibly profound, but we'll talk more about it on Wednesday when you come back. So I'll be happy to answer questions, but otherwise, have a good rest of the day, and I will see you on Wednesday.